as usual, I want to thank the organizers for inviting me here to a vast body of speakers. And people really should tell me if the feedback becomes too bad, because I can turn up the mic. Sorry? Yes. Oh. Okay, much better. All right, good. Okay, so people often ask for the slides. These are already online. You can either go straight to this web page, this web address, or it's also linked from my web page. So it should be easy to find. And here's some references if you like those references. People do sometimes. All right. So it's a fact, which I hope you guys have accepted at this point. To me, it's sort of almost the definition of combinatorics. But sometimes it's easier to think about numbers as the sizes of sets. There's some numbers that just make more sense when you realize, this is the size of a set. The factorial, it's the number of partitions. And there are various more complicated numbers that, somehow thinking about them as size of sets makes thinking about them easy. Similarly, there are some sets that become easier to think about when you realize that there are morphisms between them. When you realize that they're the objects in a category. And I'm taking the fact that these are reasonable things to do as kind of for granted as a way to open up your mind at the beginning of this talk. That sometimes it makes sense to take sets, think about them as categories. And that's not a canonical operation, but often it makes our life easier, and we know that it feels right. All right, we can take this principle and we can make it linear. So one way to say that is, numbers, well, they don't have to be the size of a set. They could be the dimension of a vector space. And of course, you can say, the dimension of the vector space, that's the size of a basis. But maybe I don't want to choose a basis. Maybe I just want to think of it as a vector space. A good example of this is Littlewood-Richardson coefficients, or tensor product multiplicities. Come up with the dimension of a vector space that doesn't have a canonical basis. Doesn't have any sort of natural way of choosing a basis. But they are good numbers. All right. The sort of bit of this one step up. So how do you linearize this idea of you can take a set and realize that it's the objects in a category? You can take an abelian group and realize that it's the Grothendieck group of a category. In the interest of time, I deleted my slide defining the Grothendieck group. Hopefully that won't cause any trouble. But it's the group whose basis or spanning set is the objects in the category, and if you have an exact sequence, the middle is the same as the sum of the two elements. So what I want to talk to you today about is how some very important objects in mathematics. I know this is a topology conference. I am often speaking to representation theorists to whom this is a little more self-evident. But semi-simple Lie algebras are very, very fundamental objects in mathematics. I want to emphasize to you, if you get nothing else out of this talk, there is a category that these extremely fundamental objects are the Grothendieck group. That itself, I think, should be a remarkable fact. I know that you're, for the most part, topologists, so you don't think that this is your bailiwick. But I still hope that sounds like a cool thing on its own, even if it doesn't have applications, though actually it does. All right. So, this sort of idea of categorification is you take your favorite abelian group and you say, is there some category under this? Of course, that's kind of a very artificial way of stating things. Obviously, usually you have some underlying idea of where this category is going to come from, why it has this structure that relates to your abelian group. It's not very effective to just start with a abelian group and say, how would I make this a category? That's kind of not quite the right approach. But in the interest of time, I will kind of introduce things that way. All right, so I'm always going to be talking about the Lie algebra SL2. There's nothing really that special about SL2. It just makes it kind of easier to write things down. So almost everything I say is going to be true of any simple finite dimensional Lie algebra. and actually even any symmetrizable Categorification algebra. But we don't need to worry about those. But just to make my life and the notation and your brain sort of go a little easier than just sticking with SL2, of course, 2 by 2 trace zero matrices with these nice generators we like, E, F, and H. One goes up, one goes down, one stays in the middle and tells you where you are, with these famous commutation relations. And of course, mainly I'm going to be interested in the universal enveloping algebra, which means the associative algebra generated by E, F, and H, subject to these relations, where I interpret the bracket as commutative. So this is a presentation of a Lie algebra. It's also a presentation of an associative algebra. When you interpret it that way, you get the universal enveloping algebra. All right. Hopefully that's at least a somewhat familiar object for most people in the audience. What's maybe a little less familiar is I need to enlarge the universal enveloping algebra. And this is going to look weird, but there's actually a very simple principle behind it, which is I want to add elements that project to weight spaces. So I want to add a new element to the universal enveloping algebra that just looks at a vector and says, does this vector have weight n? If it does, you keep it. If it has some other weight, you make it 0, and you just extend linearly to everything else. So it's a projection to the nth weight space. So this is something that acts on any of the simple representations of SLN because they're the sum of their weight spaces. And as should happen with projections to different weight spaces, if I project to the nth weight space, project to the mth weight space, and they're different, well, that should be 0, right? If I already projected to one weight, I'm going to kill everything else. On the other hand, if I project and then project again, that should be the same as just having projected once. And this commutation relation with H is exactly telling you that you're projecting to the nth weight space. That doing this projection and then acting by H is the same as just doing that projection and acting by n. That exactly says you're projecting to the nth weight space. Right? This is the commutation relation that any semi-simple matrix would have with the projection to its nth weight space. So this is nothing special about SL2. This is just picking the matrix H, looking at a vector space that acts on semi-simply, and looking at the projections to the eigenspaces. There's nothing else going on here. And then these commutation relations with E and F. And these just tell you how E and F change weight spaces. Right? E, it's an upper triangular thing. It increases how the torus acts. F, it's a lower triangular thing. It decreases it. So you exactly get these things that projecting before F is the same as projecting to a slightly different weight space afterwards. Why am I doing this? I'm doing this so I can cook up this sort of much less compact way of representing elements of my universal enveloping algebra. So I can represent elements of my universal enveloping algebra not in this kind of compact way where I just write, E, F, E. Instead, I turn each E into a little arrow that goes up, and each F into a little arrow that goes down. And I put these on a dashed line, and then I remind myself what weight space these are supposed to be acting on, which idempotent I use. So the rule is, if I'm reading from right to left, whenever I pass an up arrow, I increase weight by 2. That's acting by an E. It increases the weight. Every time I pass a down arrow, I decrease the weight by 2. And so once I've labeled one of these regions, all the other ones are fixed. All right, so there was no content in that last slide. I was just telling you a different way of representing elements of that algebra. On this slide, there is content. So Pavanov and Lauda had this idea. I should mention that somehow Schwang and Ruquier had a very similar idea earlier but they didn't draw it in this way that makes for pretty pictures. They wrote a lot of really ugly commutative diagrams, but it was kind of the same idea. I think it's fair to say that they had it first. But Bottom and Lona had this kind of picture where you think, okay, these diagrams I drew, I want to make these the objects of a category. Right? I want a category whose Grothendieck group is the universal enveloping algebra. So it should be a category where the objects naturally are attached to elements of my universal enveloping algebra. So I just take this picture, and I think I want to make this an object in a category. So I want to say what it means to have a morphism between two of these. Well, it turns out a morphism between two of these is just a picture that interpolates between them. I hope you guys have seen some sort of category defined like this at some point in the past. So a morphism is a picture like this one I've drawn here. So things that might concern you, everything is oriented. Remember, my guys at the top, whether they were oriented up tells me whether they're E or F. And E and F are very different, so I have to keep track of the orientation on everything. I have this crossing. That's not an overcrossing or an undercrossing. It's a genuine crossing in the plane. I don't get to decide one of them goes over the other. You'll also see here, I have this kind of extra decoration that are dots. That's just some morphism from E to itself. The kind of content is going to come in the relations, right? This is a morphism, but of course, the only way to make this interesting is to say that there are some relations between this morphism that we'll talk about in a moment. And I'm also allowed to have closed loops. So it says, you know, these are supposed to be oriented, I should have said immersed one manifolds, decorated by dots, and with, you know, boundaries satisfying, matching up with the guys at the top and the bottom. So I can have components with no boundary that just do whatever the hell they want. They can go anywhere. That guy could be at the far left. It could cross some of these other lines, connecting the top and the bottom. One thing I should have drawn in to emphasize is possible. You can start at the top and go back to the top. You're allowed to have cups and caps. I mean, you can kind of see that in the circle, but I probably should have included some of it in there.
So these objects, they form the basis of the that very quickly?
No, they're not a basis, they're a spanning set. There are relations between them, and I mean, I was going to emphasize this later, but let me mention it now. You know, I have to define some relations between these maps. And one of the things I want to get out of those relations is that every relation in the universal enveloping algebra now corresponds to some isomorphism between objects. So that's one of the things. I'm not going to explicitly add that, but it's going to be secretly hidden in the relations I impose on these guys. All right, so here are the relations. Believe me, this slide is even worse when I don't just do SL2. You have to also include, if you don't do SL2, what you do is you label every one of these strands with a simple root. And the relations between them depends on how what the inner product between the simple roots are. But I put this up here not because I think you're going to get a lot of content out of it, but just to emphasize there is a set of relations that you can keep in your head all at once if you put a little effort into learning. And so it isn't something completely horrible. It's something you can remember, but not something you can explain in the 2 minutes per slide that I have. I just put this up here to emphasize that I'm not pulling a fast one on you. There really are relations. They all fit on one slide. And then at the bottom here, I wrote in degrees. So these morphisms are graded. And these relations I have up here are homogeneous. So if you want, you can go to my website, pull this up on your computer, and if you get bored with the rest of the talk, you can just check that it's homogeneous. All right. Now these relations, they didn't come out of nowhere. If you kind of think in the right way about the geometry of Grassmannians or you can guess what they should be. Again, I don't have the time to explain to you where, how you get them out of there. That would be a talk on its own, but you can do it. It's not just completely made up. All right, so we want a category where these objects are diagrams on the line, morphisms are pictures like I showed you, modulo these relations. And there's one more thing I have to do, which is I have to do idempotent completion. Which means I wrote down a bunch of objects, they have a bunch of relations. It might be that one of those objects has an idempotent endomorphism. An idempotent endomorphism in some category, that's supposed to mean projection to a direct sum. Right? If you had a kind of reasonable idea of the image and the kernel of maps, once you have an idempotent, you instantly can break up into a direct sum. But in this world, that's something we have to do formally. We have to say, if you find an idempotent, you just add a new object, which is the image of that idempotent. And say formally, that if idempotents add up to 1, the objects corresponding to them are, direct sum up to whatever the idempotents were at. And the way you should think about this is what you have to do to free modules to get the category of projective modules. Right? If you want to get projective, finitely generated modules over a ring, you should take all free modules, and you should look for idempotent endomorphisms of free modules. The image of that would be a projective module. So this is like the operation of going from free modules to projective modules. And of course, projective modules are better than free modules. So I hope this can be kind of justified as a reasonable thing to do. All right. So, right. One way to say this idempotent completion is you can kind of think of everything as endomorphic, as the category of modules over a huge algebra. And this would just be taking projective modules over that algebra. Just want to emphasize that this isn't something really weird. It has this kind of funny name, idempotent completion, but it is something you should be kind of used to.
Is it related to Caribbean envelope?
It is the same thing as the Caribbean envelope. I should emphasize that, yes. It is also called Caribbean completion. It has a bunch of different names. So it's the same thing as the Caribbean envelope. So people will call a category either idempotent complete or Caribbean. And idempotent complete I just find easier to remember. Right? It actually tells you what you're doing. You're taking idempotents and you're adding new objects for them. But it's the Caribbean envelope. All right. The next thing is the universal enveloping algebra. It's not just an abelian group. It has a multiplication. And I mean, the interesting thing about it is that it has a multiplication. And in these pictures I drew, multiplication is just put diagrams next to each other. Right? It's just set them on the line next to each other. And if you try to match up ones where the number here isn't the number here, so let me actually pull out my laser pointer. If these numbers don't match up, that means you're applying projection to one weight space and then projection to a completely different weight space, which is 0. So if these numbers don't match up, the product is just 0 because of how the idempotents sit around. All right, so what is my monoidal structure going to be? Well, it's going to be exactly the same thing. Things are kind of set up so that you get this almost for free. The monoidal structure is just put these diagrams next to each other. And what's the thing you need to have a tensor product on a category, monoidal structure? Well, you have to be able to assign a tensor product to any two objects, and you have to do that in a functorial way. So that if you have an endomorphism of one object and an endomorphism of the other, you get an endomorphism of the tensor product. But how do I do that? I just put the diagrams next to each other. That's kind of the beauty of this pictorial calculus, is there's some horrible point where you have to check a bunch of relations and check that you didn't actually kill everything. But all of these operations, like the monoidal structure, are just follow the pictures. You just look at the pictures and say, what is this picture telling me to do? So it's just putting things next to each other. And the fact that this is well defined on morphisms is exactly that the relations I showed you are local. They're all of the form, look at this picture, if you see some part of it that looks like this, you can replace it with this other picture. All right, are there any questions up to now? If you ask one question, I'm going to be looking for ones from you for the rest of the talk. That's just how it is. All right, so the theorem is, if you look at this category, its Grothendieck group is this algebra U dot, so universal enveloping algebra with these extra idempotents in it. And I should emphasize, if adding these idempotents looks weird, the reason you do this is it's actually very hard to write down a basis of the universal enveloping algebra if you think of it in terms of the E and the F and the H that has positive structure coefficients. So somehow this U dot was actually introduced by Lustig, who wanted to find a nice basis of the universal enveloping algebra. And of course, whenever you categorify something, well, you get a basis that comes from the indecomposable objects. I mean, if your category is idempotent complete. So somehow we already knew that to get a nice basis, we had to do this U dot thing. So somehow that suggests also in order to get a categorification, we had to add in the U dot. All right.
So the universal enveloping algebra is like left invariant differential operators on the leader.
Mm-hmm.
Is there a natural way to see U dot as an extension of that operator?
It's not obvious to me. I've never thought about it, so maybe it's easy and I'm just not thinking of it, but it's not obvious to me. I mean, somehow, the point about this U dot is it's something that's very compatible with representations that have a weight decomposition, right? You take one of these infinite dimensional representations that doesn't have a weight decomposition, U dot doesn't act on it. But a lot of those look very natural in the geometric picture. So I'm not sure that would work.
What are these eyes there in the first?
Oh, I knew there was a typo in here. Sorry. That's all right. It's good that you pointed it out. It used to be that I wrote this talk for not SL2, but an arbitrary simple Lie algebra, and I was the simple root that guy was being labeled with. And I slowly managed to get most of these out of here. There was one I had to clear out earlier, but I knew there was one that I was
It's
missing.
just one E and one F, that's all.
Right. Exactly, yes. And you see there's no dependence on I on the other side, so you should just forget those I's are dead. That's the problem with you make one slide talk and you change it around, is there are always these weird little leftover things that, correspond to some previous notation. Oh, right, that doesn't work. So, just as an example of how this works, I mean, this is my kind of running example, the EFE. The class of this object goes to this element of the universal enveloping. And I mean, I set things up so that this looks kind of obvious. But there is real work involved because I never imposed any of the relations of U. You have to check that all the relations of U are consequences of the relations on morphisms I added, and that those relations don't make too many things zero. Somehow, the checking the relations is actually the easy part. The hard part is making sure that you didn't just kill everything and get the zero quotient of the universal enveloping. But you can do that, and indeed, you get the right thing. So, unfortunately, I'm already running a little behind, so I want to go through this relatively quickly. I just want to emphasize, how do you find relations in the universal enveloping algebra inside these relations? Well, direct sum decompositions come from taking the identity and writing it as a sum of idempotents. So here exactly I'm taking the identity on FE, and I'm writing it as the sum of an idempotent that projects to EF, and the sum of an idempotent, of a bunch of idempotents that project to copies of the identity. This is exactly the commutation relation between E and F. And so here you see the advantage of U dot. That rather than having an H here, I have n times the identity, where n is the weight space I'm acting. Right? This one sub n tells me I'm only looking at how EF and FE act on the nth weight space. And this relation is sort of much better suited to being categorified than the commutator of E and F is H. That's exactly what the U dot is there is for. So you can write H as the sum of scalars times idempotents. All right, and if n is negative, you have to move things to the other side of the equation. Because again, in categorifying, you always have to do things positively. And the problem is that sort of H isn't positive or negative. It's positive on some of the weight spaces, and it's negative on some of the other weight spaces. So you have to break it up according to the weight spaces. All right. So I mentioned on the relations slide, things are homogeneous. Right? I should emphasize, if you've fallen asleep, this is where you should wake up, because a miracle is about to happen, which is, if I have a graded algebra, the Grothendieck group of that has a Q in it. That Q is grading shape. So when I have some relation, I take the tensor product of two things, and it breaks up as this sum, I can pay attention to what grading shift those summons come in. And all my relations get a Q in them. And of course, what could it possibly be? It's the quantized universal enveloping algebra. So one of the amazing things about this picture is it's never harder to think about quantum groups. Right? The quantum groups always just magically happen if you pay attention to the grading. This, to me, it's still very miraculous. Somehow I got to go through this talk never saying anything about the quantized universal enveloping algebra, never writing down the relations, and now I can use this as a definition. I can say, you just pay attention to the grading in the picture you had before, and you will get out the relations of the quantized universal enveloping algebra. So, to me, this is one of the prime signs that we're doing something right. That this wonderful structure that's very hard to explain, the quantum group, just appears naturally out of this picture without any extra work. It's a little extra work to pay attention to gradients, but in the grand scheme of things, it's not very much work.
But the whole part of the structure is the interesting thing, isn't it?
Well, there is that. We'll get to that later.
So it's in there too.
It is in there. All right. So the first thing I want to talk about is representations. Because the kind of other hint that we're doing something right is that the representation theory comes along for the ride. Well, what do representations of SL2 look like? The way I like to index them, well, each one of them has one highest weight vector, or one highest weight line, because I can take multiples. And what representation I get is exactly determined by what the weight of that line is. All right, so we can try to just mimic this on the categorified side. So I start with an object that I declare has weight n. So what declaring something to have weight n, so this is my object, and it means I should only put things labeled n next to it. If I try to act on it by any other idempotent, I'll kill it. That's what it means to have weight n. That you're sent to yourself by the idempotent lud sum n and killed by all the other ones. And then I just let you act on it by put the diagram next to it, and I impose the relation that acting by E on it is 0. So one of the kind of structures that come out of categorifying is when I impose the relation that E acting on it is 0, I kill a bunch of relations in things that don't involve E. Because there can be maps from FV to FV that factor through something that starts with an E. And I have to kill all of those, because I killed that object E acting. So the relations look just like the ones we had before, but there are, sorry, not the relations, the morphisms look like the ones we had before. We have all the relations that we had before, but we have more of them, because we've also killed all the things that factor through something acting on E times. And remarkable fact, what I get out is a categorification of the irreducible representation, and it's essentially the only possible one. I mean, I'm skipping a few adjectives, but it basically is the only one you can do. So this is one hint, another hint that we're doing something right, that the simple representations can all be categorified, and all can be categorified essentially uniquely. And this is, again, something that carries over to all the other groups, where the structure of representations is much more complicated. There's still a unique way to categorify every simple representation. Another miraculous thing is if you know your representation theory, you should be surprised. I started with the highest weight vector. I said that E acting on it was trivial. In decategorified land, that's not enough to get a finite dimensional representation. You have to impose more relations to that than that. But they all magically come from the relations between morphisms on objects. When I kill E, I also kill very high powers of F. Because on some very high power of F, the identity map factors through one of the objects I killed. So I also kill those. So I automatically get something finite dimensional. And this, I would say again, is a sign that we're doing something right. It's a sign that we're in the right place. Yeah?
So can you categorify verbal modules then? The obvious
No.
doesn't.
I mean, you can actually prove that this version of the categorified universal enveloping algebra cannot act on something which is generated by a highest weight vector and which is not integrable. So for a finite dimensional Lie algebra, that means it has no representations generated by highest weight objects that are not finite dimensional. You just can't do it. So there are various thoughts about what you should be doing about Verma modules. It's upsetting that you lose them. But on the other hand, it's awesome that you don't need to impose the relations for them. So I mean, this is both a good thing and a bad thing. I don't know. It's a double-edged sword, but on some level, it's, I don't know. I still think it's kind of cool. All right. And again, since you're topologists, this isn't of extraordinary importance to you. But let me just mention it, because it is one of the important applications of categorifications, which is if I look at a basis of indecomposable objects in this category, that gives me a basis of my representation, which is pretty boring in SL2, but is interesting for other groups. And when I apply E or F to it, I get a new object. Well, that new object, if it's not indecomposable itself, it's a sum of indecomposables. So E and F must have positive integral structure coefficients. Right? I just take it acting on the indecomposables. So I find a basis for my representation, which has positive integral structure coefficients on E and F. And there are various other things that also have positive integral structure coefficients. So on some level, this is a very exciting result if you care about bases of representations. I think this is the first sort of good description of one for every simple Lie algebra that has a positive integral structure coefficients. You can do this in symmetric Cartan matrix using Lustig's canonical basis. And for those, you get this back. But in other types, Lustig's basis doesn't have positive integral structure coefficients. So this is something new and arguably better. Arguably. But it has at least one advantage over Lustig's basis. All right, but that's not so important for topologists. What is hopefully at least important for topologists, at least why I got invited here, I'm sure, is that quantum groups are important in topology. If you have quantum groups, well, indeed, they have this very interesting operation on their representations, taking tensor product. And this is considerably more interesting than taking tensor product of just universal enveloping algebra modules, because W tensor V is not canonically isomorphic to V tensor W. There are two different ways of getting an isomorphism between them. And along with some other structures, this can be phrased as UQ representations are a ribbon category. This basically means that if you take a ribbon tangle, a tangle where I thicken all the strands into ribbons, and pay attention to twists between them, and I label each ribbon with a representation, I get a morphism corresponding to that ribbon tangle. And of course, if I take a knot and think of it as a tangle going from the empty thing to the empty thing, I get knot polynomials. All right. So at this point in the talk, what we know we have are these two categories that correspond with quantum groups. And what we want down here at the bottom, or at least what I want, is categorifications of the quantum knot polynomials. So that would mean vector spaces with a bi-grading, such that when I take graded Euler characteristics, so you think of it as a complex of graded vector spaces, when I take graded Euler characteristic, I should get back these quantum knot polynomials, including the Jones polynomial and other ones. All right. And here we have a mystery. We want to put some categorified construction in here that will let us get there. Well, of course, what would be great is if the representations of this 2 category were a ribbon 2 category in some sense. At some level, if you could prove that, then this would just come for free. But that's pretty hard. At the moment, we actually don't know how to take 2 of these, just kind of abstractly and test it. So, I saw Ruquier last week, and he claims to now know how to do this, but, it's not published yet. Basically, nothing has been proved about its properties. So at the moment, we don't know that. I'm not even sure what a ribbon 2 category would be, but whatever it is, I don't know the representations of this 2 category are. All right, but we can ask for less structure. All we need to construct the quantum knot homologies are tensor products of simple representations and some maps between them. And of course, it's nice to think of those as all coming together in some kind of uniform categorical package, but all we really need are the maps. And those, I can tell you how to write them. So this is not as nice a construction as I would like, because I just say, okay, here's the categorification of a tensor product of symbols. Without saying, okay, take the simple guy, feed them into this universal machine, and get out this category. But I can tell you how to categorify symbols. Let me first remind you about the Reshetikhin triad quantum knot invariants. As I said, they come from the fact that V tensor W and W tensor V are not canonically isomorphic. There's this braiding isomorphism between them, but there are 2 inverse ways of doing it, which we think of as overcrossing and undercrossing. And there are also these quantizations of, so this is the inclusion of the identity element. This is the co-evaluation. And this quantizes the trace. You're looking at an endomorphism algebra, and you're mapping a trace. So this is where my crossing top and cap come from. And as usual in quantum topology, I just take a projection of my link, I cut it up into simple pieces, I take the maps corresponding to those, and when I compose them all together, I get this quantum knot invariant, the Reshetikhin triad invariant. I often say quantum knot invariant because Reshetikhin triad invariance also means invariance of 3 manifolds, which we don't know how to do at the moment. Probably in part because we kind of don't have this category as canonically as we would want. But we certainly have made a lot of progress categorifying quantum non-invariants. So this is well over 10 years ago now. Ivanov produced a categorification of the Jones polynomial. And also, I hope this is easy to see. This is grayed out. So there's this, of course, very interesting categorification of the Alexander polynomial, not floor homology. The Alexander polynomial corresponds to a superalgebra. It corresponds to GL11. I don't know how to fit that into my picture, so it's grayed out to remind you, I don't know what's going on. But Ivanov produced a categorification for SL3. He somewhat accelerated and produced one for the defining representation of SLN for all n, jointly with Lev-Rozhansky. Some work following up on that by Strapel, Mazurchuk, and Susin produced wedge powers. Work of Cottis and Kamnitzer also produced wedge powers. And there is some work of Ivanov and Rozhansky on the defining representation of SLN. So this is enough representations to say to ourselves, man, something is going on. There is, this Jones polynomial thing wasn't a complete fluke. But on the other hand, in the set of all representations of all simple Lie algebras, this is a very small selection. In particular, all of these are minuscule. There's something special about minuscule guys. I haven't updated this talk. I should also include the work of Katerina and Josh Susin and Igor Frankel, which has produced a categorification of the colored Jones polynomial, which is kind of the first non-minuscule one that would go on this list. So what I want to talk about in the rest of the talk is a way to use this categorification picture to get a unified construction of not-invariants for all of these representations. Now, that's not quite the same as saying a unified construction of all of these not-invariants, because these aren't all known to be the same. So, particularly the Milano-Rozhansky, Strapel-Mazurchuk, and Cottis-Kamnitzer all categorify the defining representation, and we don't know that they categorify the non-invariant for the defining representation in the same way. So I can prove that what I'm doing is the same as Strapel and Mazurchuk, because it's essentially, the technique is essentially copied from Katerina's papers, and thus it ends up with the same thing. But for Cottis-Kamnitzer and Milano-Rozhansky, it's unclear whether they're the same or not. But it's at least not proven that they're not the same, so I can conjecture that they're the same. All right, any questions?
What is the same, the categorification or the corresponding invariance?
Oh, the invariance, sorry. So what I've written here is which quantum non-invariant is being categorified. And this line, Milano-Rozhansky, Strapel, Mazurchuk, and Susin, and Cottis-Kamnitzer all produce categorifications of the quantum invariant for the defining representation of SLN. This is a specialization of the Hanfley polynomial. And I believe it's not known whether any of these three are the same or whether any of these three are different. So there's neither an example where they differ nor a proof that they are the same. And over here, I've indicated which ones I can prove are the same as what I'm going to tell you, and which ones it's still conjectural.
And
Yes?
back a few steps per se about the Vermas. The non-existence of the Vermas, does that have anything to do with looking at things after identical completion?
No.
No information on it
I mean,
before?
the easiest way to say it is for kind of philosophical reasons, the Euler form on your category should be non-degenerate, and E and F should be adjoint. And there's a unique way of doing that on the Verma, which is the Shapovalov form. And so you kind of see, for philosophical reasons, you need to get the quotient of the Verma for the Shapovalov form is non-degenerate, which is already the integral value. There are other ways to explain this. We can talk about it later. But it's much more simple than that. It's much more basic. Somehow you just cannot get the Vermas doing this version of categorification. Maybe there's a different way of doing it that has the Vermas in it, but for this 2 category, there is absolutely no hope of getting the Vermas. All right. So I wanted to very quickly say, why are tensor products hard? Why can't I just do the kind of spectacularly obvious thing of tensoring? I already know how to do irreducibles. Why can't I just tensor the categories? And somehow one point is, as Peter said, the interesting thing about quantum groups is how to tensor things. The interesting thing about quantum groups is they don't treat the 2 sides of the tensor product equitably. The quantum group really prefers one of them. And unfortunately, references can't agree on which side the quantum group prefers, but it does prefer one of them. So we have to have a kind of undemocratic construction that remembers the ordering on the highest weights, which taking naive tensor product of the categories would not. The other thing is, as I mentioned, canonical bases are a very good hint of how things will work. And tensor products have a canonical basis, which is not the tensor product of the canonical bases. So somehow this tells us we need to do something different. That's something different. It's actually sort of, I don't know, to me it felt very obvious. Which is, just as before we wanted a graphical calculus for things in the universal enveloping algebra, now we want one for things in the tensor product. And what this is going to be is sticking on a black line means acting by E and F. Sticking on a red line means add a new tensor factor and pick the highest weight vector in that tensor factor. So for example, this picture here means I start with the highest weight vector for n2, I act with f, I add on a tensor factor of n1, and take the highest weight vector there, and then I act by E on the whole thing. So again, I'm not treating the 2 sides equitably, because it is kind of a natural operation to add on a new factor with the highest weight vector at the left, and it isn't a natural operation to do that at the right. So somehow the fact that before, when I drew my pictures, things in the universal enveloping algebra acted on the left was important. It kind of remembers some directionality. And so I put these red lines down, and I'm going to turn these into a category where I don't let these guys change order. The point is, the order these red lines show up in the plane remembers the order I took the tensor product in. All right, so just as before, we can make these into the objects of a category where the morphisms are diagrams, and the only thing that's not obvious is what are the red strands allowed to do, and they're allowed to cross black strands, they're not allowed to cross each other, because they're supposed to stay in the same order. The tensor product is supposed to remember the order these guys take. All right, theorem. This category is the right Berkeley group. And again, this is a general theorem that works for all symmetrizable Kac-Moody algebras. And indeed, what you get back is Lustig's canonical basis of the tensor product. All right. So now what I want are the maps I need to build my non-invariants. I want to take the braiding, the cup, and the cap, and I want to turn these into functors between these categories. Again, I don't know, this to me it felt like the most obvious possible thing to do. I mean, one tricky thing is you have to replace this category L with the category of complexes in it up to homotopy. So you can think of this as this is the category of projective modules over some algebra, and you have to work in the derived category of modules over that algebra. Or you could really just think, okay, I'm going to take complexes in this guy to homotopy. That doesn't change the Grothendieck group, but it gives you a lot more functors than you had before. Because now you have functors that can send just straight up modules to complexes. All right, and indeed such a functor exists that induces the usual braided structure of the Grothendieck group. And I want to emphasize, writing down this functor is much, 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 much easier than figuring out what the braiding is. The functor is just this. You look at this picture, and you say, ah, that's a bimodule. You know, the morphisms, where the red strands are in one order, act at the top. The morphisms where they're in the other order act on the bottom. And if I'm thinking of things as modules over an algebra, I can just take tensor product, and it will switch the order of the red strands. And the reason I have to pass this homotopy category is actually I should take derived tensor product. So if you want to sort of state this in kind of a proper way, I should think of this as an object and resolve it by tensor products of projected modules over this guy and projected modules over this guy. But the point I want to emphasize is the braiding comes from a very simple idea which should make topologists happy. The braiding comes from just cross the damn strands. Just cross them. Do everything as you did before, but allow one crossing between this pair of strands in your pictures. And everything will work out. Again, this is something of a miracle. Yes?
Does that crossing interact in any way with your pictorial relations?
Not really. Things just kind of slide through. I added this appearance of being an overcrossing in response to your question the last time you saw this talk. And somehow this overcrossing here doesn't actually tell you any information about the relations. The over versus undercrossing is do you take tensor product or not with the bimodule. Those are adjoint, so they're inverse to each other. And so the over versus undercrossing thing is just that doing this functor twice does not get you back to the identity. So it's not its own inverse. And this again is, I should emphasize this is something of a miracle. One of the first talks I gave on this was in Stony Brook. And one of the audience members sort of said, wait, the whole R matrix is in that picture. And I said, yes, the whole R matrix is in that picture. And he said, I don't believe you. But it's true, the whole R matrix is in this picture. And if you have ever tried to write down the R matrix, you will appreciate that this is a remarkable fact.
So can you please explain again why this picture is a bimodule over this and sigma?
Okay, so the good way to think about this is, I told you this category and I told you some morphisms between objects in it and said, take the idempotent completion. Well, that's the same as saying, okay, think of these diagrams as an algebra where multiplication is stacking. If I can't get the ends to match up, I get 0. And look at projective modules over that algebra. So this is a bimodule over that algebra. Because I can stack diagrams where the red strands are in one order at the top and where they're in the other order at the bottom. So it's a bimodule over the two different orders on the two different sides. But one does have to think about not just projective, but all modules over that algebra. Which is, either replacing this guy with this homotopy category or starting to think about algebras and allowing itself to have all modules.
Ben, could you say a little more about the R matrix? Where does the braiding emerge from?
Well, okay. So, I'm not sure I understand how to answer your question. In one way, one interpretation I could make of your question is, how does one prove that this is the R matrix? Is that a reasonable interpretation of your question? Or were you asking for something more basic?
Well, the R matrix, to me, has something to do with the
they switch orders. So right, these guys correspond to the factors in my tensor product.
Oh, I missed that there was a break in one of those red lines. Is that important?
It's not actually important. It's just to kind of remind you that this guy doesn't square to the identity. And if you do this twice, you will get some interesting automorphism with your derived category, not the identity. And I mean, how you see this as the R matrix is you prove kind of on abstract grounds that it commutes with the action of the universal enveloping algebra, and that it does the right thing on a few vectors, and then you say, the only endomorphism, the only interjoiner from this representation to this one, that does the right thing on this set of vectors is the R matrix. So somehow you don't pull the formula for the R matrix out of it, that would be hard. But you prove it satisfies properties that only the R matrix can satisfy. Yeah?
I'm trying to ask a question again. I'm sorry.
No, it's fine.
Last time I forgot the answer. So you said something about, so are you imposing relations that look vaguely like a Reidemeister 3 with 2 restraints in black? Is that what you mean by sliding over?
Yes, yes.
Okay, so there's details expressed from your talk about how that crossing is.
Sure. But this crossing behaves in the simplest way you can imagine. There are slightly more complicated things for how does Reidemeister 3 happen with 2 black strands and 1 red. But with 2 reds, nothing interesting happens. All right, so I have 3 minutes left, so I think I should move on. Similarly, the cup and the caps come from a very natural bimodule. And again, one of them comes from tensor product, one of them comes from because they're supposed to be adjunct. So yeah, just stare at this picture a little bit. Somehow this is 2 dual things being created. And the thing that goes in here in general is going to have to do with reduced word for the longest element of the biology. Of course, in SL2, that's very simple. So the point I just want to get across is these functors come from very natural pictures you can write down. Of course, you have to do work to prove that they have nice properties, and there's a lot of work involved in composing them because they involve derived functors. But somehow you're led to them by doing the easiest thing possible. All right, so as before, we just take our knot, we cut it up into its elementary pieces, and as we compose the maps before, we compose the functors. And so for a knot or a link, we just get a graded vector space. We get a functor from the category of complexes of graded vector spaces to complexes of graded vector spaces. We apply it to the one-dimensional vector space. We get a complex of graded vector spaces. That is our knot homology. And indeed, it's a knot invariant, and it has the right characteristic. And I just wanted to mention, I mean, unfortunately, I don't think Witt is here, but somehow the connection this should have to his picture is that these categories come up from deformation and quantization of quiver varieties, or for affine Grassmannians. That somehow it should come from taking affine Grassmannian, putting a Poisson structure on it, blowing it up into its Poisson leaves, quantizing those, and looking at modules of those. And all right, so this is my last slide, almost done. So last night, I was actually somewhat accused of possibly killing the field of knot homologies. And I maintain that that is very not true. And just to prove that, I wanted to put up a few thoughts about where one can go with this. Well, one is functoriality. The great thing about knot homology is it's functorial. This is very important for actual applications in topology. So one great place to go would be to prove that these guys are functorial. Now, there are maps I can write down if the representations are minuscule. But in other types, I don't even know what the maps are. And even when I can write down the maps, the relations aren't checked. So I have no idea whether it's functorial or not. And of course, course, once you do that, you should look for generalizations to the S invariant. And I in part wanted to include this because this is our connection to Mike's work. He and some other people wrote this paper about how to try to use the S invariant to find counterexamples to the four-dimensional smooth quadratic integration. And it's at least theoretically possible that if we understood these categorifications a lot better and could get S invariants out of them, they could well be stronger than the S invariants just coming from Pavlov topology. That's certainly the sort of most obvious direction to go to connect to classical topology. It's also very interesting to try to categorify other constructions in leaf theory. For example, I'm currently working with Katerina on how to do this with Q-Fox space, involving affine categorifications and cyclotonic Q-Sure algebras. It would be very interesting to do quantum groups and roots of unity, because of course that's what shows up in three-manifold invariants. And Lana wrote this short paper about 5 years ago, kind of setting up what it should mean to categorify something that's a module over the cyclotonic integers, but somehow the diagrammatic picture doesn't fit in there. Somehow you're going to have to tweak it somehow. It's a little unclear how to tweak it. Obviously, I think the biggest question, maybe I should have put this at the top, but because it is the question is, where are the three manifold invariants? Where are the extended TQFTs? How do you kind of find enough symmetry to do that without having to do horrible, horrible, horrible calculations? And finally, at least a couple of people have asked about this in the talk. Judging by audience reaction, this is actually the most interesting open problem in the talk. What happened to category O? Where are the Verma modules? How do you get them back? All right. Well, thanks for listening. That is one thing which is not proven, but there are issues at much more basic levels than that. At the moment, for example, I think it's not proven that the move where you take a circle, you split it in two, and you split the circle satisfies associativity. That's equivalent to some X algebra being commutative, which is not proven outside of